So you shoot something up at escape velocity, and by the time it reaches infinitely far away, it has stopped. Okay. Well, really, long before that point, you are so far away, the chance of you coming back is going to be pretty close to zero. And in fact, in the real world, you don't have an isolated body. There's other planets and stars and things out in the universe that are pulling on it. So there is some distance out here which is not going to come back. So technically, a tiny bit less than escape velocity could get you away from an object. But just for the sake of argument, let's say that we shoot something upwards with an initial velocity that is slightly greater than escape velocity. That means when it reaches an infinite distance out here, it's still moving with some final velocity. So I want to know what would be that final velocity. So let's do a particular example. Again, let's say we're shooting something upwards from the surface of the moon, because we've already done the moon several times here. So back to Earth's moon. So we know that the moon has some initial radius and then has a mass. Okay, so the mass of the moon is as before 7.34 times 10 to the 22nd kilograms, and the radius is going to be 1.738, and that's times 10 to the 6 meters. And we know from before that the escape velocity happens to be 2.43 kilometers per second. Okay, so I'm going to say, what if we shoot something off at 2.5 kilometers per second? So a little faster than escape velocity. So I want to know how fast is it moving once it has escaped. Okay. So conservation of energy, because this is gravity, so energy is going to be conserved. So we got this thing shooting upwards like this. So we know the initial 1/2 mv naught squared. We know that the initial potential energy is minus gm over the initial r. Okay, minus gmm over the initial r. The final potential energy is 0, and so the final energy, the final kinetic energy is 1/2 mv squared. And so we look at this and we say, well, gosh, that's pretty straightforward. We can cancel the m's. We can multiply both sides by 2. And so we'll have that v squared equals v naught squared minus 2gm over r. So to get v, we just take the square root. V naught squared minus 2gm over r. Well, we have all those numbers. So if we plug in those numbers that I gave you before, what you come up with is 785 meters per second. So that's how fast it's moving, which is a pretty good clip right there. So that means you don't have to get much above the escape velocity, and you're still moving at a pretty good clip once you get away from the object you're trying to escape from. And so this would be the example problem, because we've now done several things. We had the moon, we shot something up, we did the initial case in which v naught was less than the escape velocity, and we found the height it came to. That was the first time we approached the moon. And then we calculated the escape velocity for the moon. And so at that velocity, it goes infinitely far and stops at a distance of infinity. And so that's the minimum speed you have to be going in order to escape from something. And then this last problem we did, in which we found how fast would you be going if you launch at greater than the escape velocity. So these are the 3 different regimes for this problem. Okay, we did it with the moon, but we could have done it with any kind of celestial. In fact, this is something in astrodynamics that we have, for example, the solar system. And so we have the sun, We launch something from Earth, and we get it going at such a speed that it's leaving the solar system. And so we need to find out what's the escape velocity to leave the solar system if you start a distance of 1 AU from the sun. And it turns out that's an enormous velocity. In fact, it's bigger velocity than we have rockets. And yet there are 5 objects that are currently leaving the solar system. We have the Pioneer 10 and 11, and we have the Voyager 1 and 2, and we have New Horizons. So 5 spacecraft are leaving the solar system. How are they doing it if the escape velocity is so big? Well, we cheat. We send them to Jupiter. So Jupiter's orbit is out here. Jupiter is the biggest thing in the solar system other than the sun. Jupiter orbits at a distance of 5.2 AU. And so what we do is we send it to Jupiter. Jupiter's gravity grabs it, pulls it in, but we aim it to miss Jupiter. So it misses Jupiter, but Jupiter's gravity still accelerated it. So now all we have to do is have Jupiter accelerate it to the point that at this point it's moving faster than the escape velocity from a distance of 5.2 AU. And so that's how we got these spacecraft. The Pioneer 10 and 11 spacecraft, and the Voyager 1 and 2 spacecraft, and New Horizons. That's how we got them to achieve escape velocity from the solar system.